Thank you, Pandu. Hello, everybody. So this is more of an introductory topic, foundational topic. So it should have been early on in the workshop, but there were some scheduling problems. So feel free to ask questions and interrupt. And so the bulk of this talk is joint work with, that is working, yes. With Agilos Kiayas, Nikos Leonardos, and Yorgos Panagiotakos, but I'll also be mentioning in the second part more recent stuff. Okay, but the objective is to focus on these basic aspects, define some basic properties, see how we can use them to prove higher level properties of applications, and then see what are the real requirements, and contrast them to the classical notions of distributed computing, cryptographic protocol, and so forth, because there are some new elements here. Okay, so this you already saw, motivation and so forth, so I'm gonna go very fast. So this was a motivation, digital money transfer, for which you have to implement the ledger, and you can represent it in an abstracted way as a blockchain, where each block, as a bunch of blocks, where each block would contain the transactions. Okay, the transactions could be simple, Manoj sends me money, or more complicated, and you heard the notion of smart contracts, right? These programs are going to be running in around the system. Okay, so, and if you do this, the fund transfer thing, then the content is provided. You have to have enough funds to be able to do the transfer. And this is open unless you add some additional technology on top, which you probably talk about enhancing privacy and so forth. Okay, but so far, Bitcoin at least is open. And it's immutable in the sense that under certain conditions, an adversary should not be able to modify contents. Okay, basic motivation, and there should be a notion of growth or update rate, where this thing keeps growing and new transactions are being added. Okay, that was the motivation, and so. Which brings us to decentralized payment systems. I said this concept is open, but in particular pseudonymous, so that transactions have some, you see accounts transferring funds and so forth, but those are pseudonyms. Right? It turns out that early on there was a notion, eCash, that you might have heard of, introduced by David Shaum, that had strong, privacy guarantees in terms of you won't figure out who the participants are. Except that this was centralized. It was designed to couple with the current banking system where everything is centralized. And it turns out that Bitcoin is the first decentralized cryptocurrency, meaning it's a peer-to-peer network, no central bank, no depositor insurance, meaning if you lose your funds, you lose them. And you sort of have to maintain this public transaction ledger that we saw in a distributed manner, right? So history, as Pandu mentioned, around, so the paper was filed in 2008 by Nakamoto. In January 2009, the network took off, and it has had a high impact with a number of other applications besides funds, transfer of funds. And briefly remind you what the parties are. So we have these parties called the miners and the payers. Those are the guys moving funds or reading transactions and so forth. But these are the guys who are supposed to maintain the distributed ledger, and they have to do work. And we're going to see what this work is about. And why do they do it? Because they get fees, they charge fees for installing transactions from these guys. And they get some reward. You are able to generate a new block in the blockchain. And these guys, what they do is they broadcast in quotes, and that will become clear later, saying that I'm going to, there's a transaction going on, I'm going to send Bitcoin, for this guy to generate, he has to generate an account, a Bitcoin address, all right? And then you have to verify that this address is credited, and this you can do it on the blockchain because it's open. And the security relies on digital signatures, which we'll see next. This slide that I borrowed from a presentation by Mark Stevens. So this is just the account business, how security works. It's based on elliptic curve, this elliptic curve, and the account has private key, public key, all right? And the Bitcoin, your address, your account is the hash of the public hashes of the public key, and this is an example. And you would have to use the private key in order to say I'm authorizing, I'm sending this Bitcoin to other party. And the wallet may contain many private keys, public keys. A transaction would look like this. This account is moving funds to this account, all right? And here's an example that you probably were Alice, Bob, and how do they transfer funds from one to the next? First, Alice sends to Bob, then Bob gets it and then splits it and sends to Charles and keeps the remainder. Okay, so just an example. Are the slides available or just the YouTube?
Slides will be
okay.
Available.
All right, so then you can read them more detail because some of the proofs I'm going to skip. Okay, so we talked about these transactions. we need the notion of a valid transaction. And these transactions, as I say, are organized in a ledger. And they should be depending on the application, a well-defined public predicate that says this transaction is valid. Right, so call that the predicate valid, and this means we have a ledger, a transaction, manures that we have enough funds to send the money, so the transaction should be invalid. And each miner will accept transaction based on its local view of the ledger. All right, so what is needed for this thing to work is that a payer should not be able to do this. It's called double spending, use the same funds to pay to two accounts, and that means that if only one of them should check out, right? The predicate applies to these transactions, only one of them should say valid. Okay, so that's cool. So no honest miner will accept an invalid transaction. Okay, so we're talking about distributed implementation of this. So as long as everybody had the same view, right, this should work. I mean, if it was just one party maintaining the ledger, it's easy to do if the party is honest. But if the parties agree, then double spending should be infeasible. Right? As I said, single miner, this works. But now we have multiple miners. Okay, we want to prevent double spending, and we have a bunch of miners maintaining this thing. And in such a permissionless model, okay, where you don't know exactly who the miners are or who's running the system. And this is sort of contrast with the traditional stuff, because it is not a traditional distributed system which are permissioned. Okay, so distributed system, everybody knows who the participants are and who's talking to whom and so forth. And these are some examples of distributed systems. There's a vast literature on fault-tolerant distributed systems. You might have heard of something called Paxos, which is a fault-tolerant distributed system, an improvement called Raft. But this is all benign failure. There's the Byzantine version of these things where some of the parties might be malicious. And of course, in crypto, we have secure multi-party computation, which in some sense is bigger, subsumes this fault tolerance business. Okay, that's the traditional thing, and there's permission, but in the permissionless model, we don't know the participants. We don't know who's participating exactly, not even their exact number. Okay, how many people are participating? It's dynamic, nodes come and go, and it's open. Anyone can join. And still, what you want to do is realize this distributed ledger where parties get the same view. All right, so here's a pictorial. So we're trying to do this. Right here, all transactions are centralized here, and here we have a bunch of transactions going to all these parties, and they have to communicate and try to emulate this central ledger. Okay, and what are the properties of what a ledger should have? One is, as I say, same view. All right, so everybody should be looking at the same thing. And it should be meaningful, it should be live in the sense that transactions would keep, you should be able to insert new transactions. All right, and we'll get back to a more formal definition of this robust distributed ledger object. Okay, so distributed ledger, and so we mentioned the permissionless model. And it turns out that in the classical literature, there has been some, people been looking at related problems. For example, it is known that without authentication, there are strong possibility results. You cannot do much. Okay. Also, no authentication, Sybil attacks are unavoidable. Do you guys know why Sybil attacks are called Sybil? So this is a pseudonym to a real patient that had a multiple personality disorder, which always reminds you of this movie called Split. Do you guys see that movie with James McAvoy and Manoj? Did you see that movie? The guy has like 23 personalities, a woman, child, but the 24th one is the bad one. It comes. The beast, that's what it's called. Okay, so multiple personalities, and the thing is, if you are in an unauthenticated environment, you don't know who you're talking to, right? So the guy might pretend that it's different parties. Okay, so this was called Sybil by Dusser in the early 2000s, and in fact, also in the classical literature, it's known that there's 1/3 barrier that you can tolerate. And this is for a consensus, the consensus problem, which we're going to get into. All right, this is called by Borcherden back in '96. All right, so we have this 1/3 Sybil attacks. We cannot do much. And still, Nakamoto came up and said, well, you actually can do things. Okay, and you can do using this object called blockchain based on proofs of work. Okay, and in fact, he claimed, well, it realizes the distributed ledger thing that we're trying to realize, and assuming an honest majority of computational power, assuming an honest majority. All right, so now notice the contrast between the 1/3 and the 1/2 already. Okay, you can do things that we knew in the classical world we cannot do. All right, so that was the introduction. So this is the plan for the rest of the talk. This I should try to get through this in the first part, the first hour, and then talk about this in the second part. In the first part, we just talk about the basics, how to do this abstraction, the Bitcoin backbone protocol, which has some with the properties that we identified. And in part two, we just look at what we call applications, things that you can do on top of this underlying data structure, in particular this robust transaction ledger that we mentioned, how to realize that. And then a bit more advanced topics, such as, do we really need a Genesis block? Okay, which is how Bitcoin started, and we're going to show that you don't. And I'm also going to mention most of the stuff that I'm going to talk about works in a setting where parties are not known, but their number is fixed. Okay, so that's not, Bitcoin, we say, is a dynamic thing. So this is like a first step. Then I'm going to mention some results when parties come and go. What can you state about that situation? Mention also briefly, all this assumes a cryptographic analysis. What happens if you do more of a rational game theoretic analysis? Okay, so parties that are corrupt may not behave arbitrarily. They just, they're very focused. So they want to make money. Okay, so we're going to show how the bounds change in that situation. And finally, the focus of this talk is on proofs of work. But I'll mention something about proof of stake blockchains, because there are some new, which you already saw during this workshop. But there's some new element here, and then I'll give you some references for you to look at. All right, so what is a blockchain? We already saw. Parties, the miners do work to install transactions or organize in chains of blocks. They look like this. And you can think of this block as having this structure, hash of B1, so link to the previous block, data, okay, and then a proof of work, which we'll define more formally. All right, and the data will be this type of transactions that we saw earlier. All right, and this is called proof of work, also AKA crypto puzzle, which go back to this notion introduced by Dwork Naor called moderately hard functions. Okay, there's more other works that followed up. But you can think of this as being a proof of work being a polynomial time predicate, which two arguments, okay, these are stuff that you're concerned about, like it would be the transactions in the proof of work, and you have to find the second argument in this witness space. Okay, and typically you would like this to take a long time, and you would assume that if you want to prove something that there's a lower bound. And importantly, verifying once you've found this witness, verification is very easy, all right? And you don't always get a solution, because you might try, you might do work, but you only succeed with small probability, which is important for this whole thing to work. Okay, and we already mentioned this has been used for civil attacks. The original motivation was spam mitigation, also denial of service, but arguably the most impactful application is what we are talking about today, this design of blockchain protocols. Okay, civil again. And as I mentioned, we're going to be doing, we're focusing on proof of work for now. And this is how a proof of work would look like. Okay, so this, you can think of I-1 of the transactions at that point. Okay, this is a compressed version of the previous state. Okay, all this is hashed. And there is the witness that you look for so that when you hash the whole thing, it's less than a threshold value. Okay, so there's a basic notion of blockchain, and we'll be more specific later. And in this context, so as I say, miners might have their own version of the blockchain, right? And when they get a new blockchain, somebody sends stuff, they choose the longest they receive. And also, we mentioned there's a transaction here, and to avoid double spending, and for that you would need that if this transaction is stored in this block, you would be able to generate a detour so that this transaction is erased, disappears. Okay, so in that case, you're going to be able to spend the funds again. All right, but in order to do that, once things sort of stabilize, once the transaction is sufficiently deep in the blockchain, this is not possible unless the adversary trying to do this has a majority hashing power. Okay, so more about how to use POWs. As we mentioned, we collect all these transactions, called this boldface TX. Okay, and this is, miner is trying to insert it into the blockchain by doing this and finding a witness. Okay, and keep going, exhaustive search, brute force. And the t value would be, with a bunch of leading zeros, so it would be a much smaller, value than the whole range of the function, okay, which makes it more difficult. And in Bitcoin, this hash is, SHA-256, and further on in our analysis, we're going to model it as a random oracle. Right? So if a miner is doing this and is successful, meaning it finds a witness, it's going to broadcast this stuff, and that's a new block. Because so the guy won, he's going to get rewards, and then the blockchain is going to get extended. And as I mentioned, we're going to be modeling for now this as a random oracle, and I'll give you a point of some other reference later. Okay, so if you are sitting there and you see a new blockchain, you check that the last block checks out, and it's easy to verify. Verification is fast. If it does, you extend the ledger by adding this block. Again, if you're talking about the ledger application, then the ledger would be extended with the new transactions. All right, and what happens, as I already mentioned before, you're sitting there, you have your own blockchain, and you receive a new blockchain. So you move to that blockchain if that blockchain is longer. It's valid, right? So it passes inspection and it's longer. And so let us see where we were when we started looking at this formalization. So there was the Nakamoto paper, some other write-up that said that this you can use the proof of work chain as a solution to the business in general's problem, which is the consensus problem. I will talk about that in the second part. And there was more analysis by these guys, and we'll mention the Yale-Cyril paper later. Okay, but what the outstanding questions back then when we started looking at this was, so, okay, what are the properties of this type of protocol? How does it implement a robust ledger? What's the relation to consensus, based on the general consensus? And to do that, we had to lay out a computational model, trans assumptions, and the cryptographic tools that were used. Okay, which brings us to this Bitcoin backbone protocol. It's a blockchain, it's an abstraction. Right, and what I like to think of as a principal approach, all right, for the design of these protocols. You want to look at the blockchain thing, what properties are satisfied, and how can you build application on top of that. All right, questions so far? Okay, so in this backbone project, we looked at, so it was a bit confusing whether, adversary was motivated to do something, or so we took a cryptographic approach and say the adversary they're going to be good guys following the protocol and bad guys corrupted by an adversary, and they can do whatever they want, right? So it's a cryptographic analysis. And we call it backbone because we're going to analyze the core of the protocol. It's something the data structure layer, and forget about the fund transferring application. And to do that, once we had this core analysis, we could define applications by basically using 3 functions. Okay, the application would have a validation predicate that we mentioned, meaning if I wanted to install a transaction, I look at the block, the ledger, this guy should have sufficient funds, for example. We should define how the inputs are stored in the application, and there should be a reading function, an output function. Say, well, I want to see the content of the ledger, this is your output. So it turns out that if you specify this, you can specify a bunch of applications, in particular, a robust transaction ledger, right? So this way we distinguish the data structure, the blockchain part, and the properties it satisfies from the application layer. All right, so for that, do some sort of analysis, we need some sort of network computational model, which we draw from cryptographic protocols, circular multi-party computation. And as I mentioned in this part, we're going to start looking at the fixed number of parties. Okay, it's not known what n is, okay, but the number is fixed. And the adversary can be cryptographic, and never mind if you don't know all these terms, but the guy can do whatever he wants. He can deviate, not run the protocol, lie, and so forth. So that means that if we have some security statement, it's going to be secure against all possible attacks. Right, so how about communication? We mentioned peer-to-peer before, so it's not a fully connected graph, as most of the classical literature assumes. It'd be a peer-to-peer type network, and messages then would be delivered through a diffusion type mechanism. Think TCP/IP. You plug something into the network, and the thing diffuses. Okay, but the actual the connectivity is going through my neighbors, right, and then it spreads. And sometimes we call that broadcast, but it should not be confused with what we call broadcasting crypto, which we'll come back to in the second half. We mentioned permissionless, so there are no identities here, right? So parties cannot authenticate each other, all right? So it means that the adversary can pretend that he's spoofing addresses, the source of the message, and for now we assume that it cannot disconnect parties, all right? So it can spoof, but the communication medium is reliable. Okay, if a party is sent, it's gonna get to everybody. And in this first abstraction, we assume that the time is divided into rounds. Okay, where in each round, all messages are delivered, sent in that round are delivered. Okay, you can think of a round being something like, 10 seconds, where all the messages get delivered, and during those 10 seconds, you do some computation on stuff you receive, and then you send it again, and a new round starts. And this notion, this synchrony notion is sort of relevant in the sense of if you're going to be using proofs of work, so time has more meaning than in other contexts because, there's a notion of limited, stuff that you can do in a certain amount of time, right? And so this is a first approximation, but it turns out that the analysis extends to so-called bounded delay model where, you send a message now, it might get to you like 3, 4, whatever rounds later. Okay, and there would be a bound, maximum bound, but parties might not know what the bound is, right? And this is a model that Dwork, Lynch, Stockmeyer introduced back in '88, and they call that partially synchronous. But it's still a synchronous network, right? And this is what Paz, Shelat, and the other is. Consider after we did this work, they showed how to formulate this stuff in this model. All right, so that was a network. So we have rounds. What we assume here is that in each round, the parties, we saw this hash function, so see, it's going to be a limited number of times that in a round, the party can invoke the hash function, and we call that, arbitrarily, we call that Q. So you have Q queries to the random oracle. When you do this exhaustive search for a witness, you have about Q, so the maximum number of it can do in, say, 10 seconds. Okay, thing 2 to the 32, invocation of the hash function with, different arguments. And we're going to be assuming a flat world, meaning all the parties for now have the same computational power, so every party is going to have a Q bound, all right? And that means, and the other side is going to be able to corrupt a bunch of them, call them T. Okay, so the aggregate number of queries the adversary can make, and the adversary can coordinate, right? Looking for a solution. Could you look at this section, look at this segment, and so forth? So we have this many queries per round, and in the flat model, then you can map computational power to number of parties. Okay, so in order to compare it with the classical results, right? So this means that if T is less than n over 2, the computational power of the adversary is less than majority. Okay, and intuitively, this situation, the adversary corrupts parties and they can coordinate, but the honest parties go solo, right? They're doing their own thing, so they're in worse shape than the adversary. And for now, we're going to assume some sort of what we call in crypto trusted setup, which is an unpredictable genesis block, and think of a CRS, common reference string, the trusted party, publishes at some point, and everybody starts using it. And later, we're going to see that this is not needed. All right, so given that model, now we can say more about the Bitcoin backbone with the functions that we mentioned. For example, the context of C is a chain, have to satisfy this predicate. If a party sitting here has this chain and receives this chain, it's going to take it because it's longer. And finally, when a player is requested, party player is requested, the contents, it will return R of his contents. Okay. So we have this thing, we have the model, how things are going to work out. So what are the basic properties that such a blockchain would satisfy, and we would like it to satisfy? And these are the properties we came up with. We're talking about the chain, so this should be a common prefix, right? And that captures all this notion about agreement, consensus, and so forth. Meaning that all honest parties, should be looking at the same prefix. Okay, and that prefix, after some time, some rounds have passed, this prefix is going to be immutable. Another property we came up with is see how much stuff honest parties can insert into the blockchain given this network and computational assumptions. Okay, so we want to figure out what's the proportion of good stuff that is going to be in the blockchain. All right? And another important property is that this chain should grow. Okay, we have some sort of measurement of, parties are working, and this is related to the liveness condition of the application. Right, parties are working, they should be able to, the whole system should be able to make progress. Right? In fact, originally we just thought about these two, and we used this implicitly, but it was shown later that if you had this property, then you can prove things about applications in more modular, black box way. Right? So common prefix is saying, there could be a lot of transactions where they diverge, they have different views, and this, you can think of this as an environment providing input to the system, right? So it's providing inputs to miners, but we notice common prefix would mean that, you have this thing, it's a mess at the end, things might be looking at different things, but they should be common to everybody. The combined view, they are looking at the same prefix. Okay, and it has a more formal definition. So if two parties prune sufficiently many blocks, they get the same prefix, and it can be expressed as this. So R's are round numbers. P1, P2 are two arbitrary parties. They have C1 and C2. And this is saying, I have C1, right? I shave off this, like shave off the last K blocks. This should be a prefix of C2. Okay, but I write it this way, C2 could be C1 and so forth, and in fact, C and C1 could be the same. The property was later identified as self-consistency, right? So you have this prefix, you should not be able to move away from that, right? And this is where there are two different rounds. Okay, so that's a common prefix property. Chain quality is, I don't have a picture for this, but this is saying, honest parties are doing the work. Will the corresponding blocks be accepted into the blockchain? And we have this parameterization, mu and k. So k is you take a k-long subsequence, Okay, you want to think about the fraction that the adversary, might have. And we want the content introduced by the adversary should be less than mu k. Right? So you have this property. And the blockchain grows, saying, well, time goes by, so the chain should grow. And is expressed as follows against 2 rounds, honest party, chain C1 and C2. By the 2 rounds, then the chain grew by this much. Okay, so S here is the time that's passed, measured in rounds, and tau is the amount, the number of blocks that it should have increased by. All right, so a bunch of parameters just to formalize these properties, and then the notation gets a little bit more complicated when you do all this. And I'm going to sort of flash it, okay, but you can look at the slides later and read the paper. Yeah.
Simply the difference in coordinate.
Yeah, the difference. So chain quality is going to tell us of that growth, how much, what proportion the adversary was able to, what's the bound on the number of blocks the adversary was able to insert and so forth. But this thing is growing. Okay, so we want to see under what conditions these properties are going to hold. We have a bunch of parameters. We're going to have a security parameter that's going to be, the size of the range of the hash function, say. Okay, we want to have this to hold these properties with overwhelming probability in that security parameter. Because these properties, as we stated, should hold with overwhelming probability. And once we have that, we would like to, the properties also are going to come with applications. We already mentioned distributed ledger have this consistency, liveness conditions, right, these properties. So we should be able to derive these properties from these underlying properties. And the proof strategy goes like this. First, we're going to come up with a notion we call a typical execution. Then, so typical execution should be a typical, we would like it to be an execution where the honest guys overpower the bad guys, right? So everything works, assuming a honest computing majority. And when would that happen? I mean, we're going to show that this happens, almost always. All right, and when we have those executions, typical execution, so we don't care, if it's not a typical execution, we give up, but those are going to happen with negligible probability. Now we focus on typical executions, and then we prove these properties, common prefix, chain quality, and so forth. All right, and then derive the application properties modularly. Okay, so now it gets a little intense in terms of notation, but we'll see. So we already mentioned N, the number of parties, and the adversary corrupts T. So these are honest parties, T bad parties. We want honest majority. How do we capture that? We want to say that the honest parties, are bigger. The number of honest parties is bigger than T, all right, by this much. All right. So for now we don't care. But think of lambda being, 1 or bigger, and that means that, this is going to be, n minus t is going to be more than t. Right? This lambda is going to come up later. T we already saw is the target hash value. Kappa security parameter is a range of the hash functions. Q number of proofs of work.
Epsilon and the delta you have.
Yeah, so it's going to be typical, this is going to be our negligible probability type thing. We're going to we're going to parameterize the error by epsilon, but that's going to be the. And now notice what happens when you do one query to the random oracle, right? You're trying to find a witness, right? So you just choose one guy. So the probability, and if you model this as a random oracle, then the probability of success of your query is going to be, the lower threshold t over the whole threshold, right? It's a random process, right? You pick a random guy, it's going to be at random, right? So it's going to be in this range with probability, t over 2 to the kappa. All right? And importantly, one important measure is going to be what happens when just one honest guy gets lucky, solves a proof of work, finds a witness, all right? Just one guy, for simplicity. There might be more than one honest guy doing it, but when just one guy is successful, the whole system converges to the same view. Okay, that's why this event is important. All right, and we're gonna compare this event, just one guy getting lucky, with the probability of the adversary, getting lucky. Right, and as long as we can guarantee that the expected value of this event is bigger than the expected value of this event, right, the honest guys, the whole thing is gonna work. So now you can do this if business that appears in a few places to denote the probability of at least one guy, honest guy getting lucky, right? That's why you have the A minus T. That's why the guy Q, that's the total number of queries. And this nobody gets lucky. Nobody gets lucky. 1 minus that thing is a probability of at least one. Okay, and if you do the computation, you get something like this. All right, and now this is at least the probability of exactly one honest party. You get a more complicated expression. Okay, which is it's going to look like this. Yeah, so we say that each party, we assume that each party, the computational model is flat, and that in one round you have about the number of attempts to you can call the random oracle so many times. That's Q. When you call the random oracle, when you call the hash function, that will be a POW attempt. The Q is the bound. So the Q is the maximum number of calls that you have. Every party is flat, so everybody has Q, the trials, right? So they can attempt Q times to do this. As I said, the adversary is corrupting a bunch of guys and is coordinating them, right? So if you're looking at the same thing, right, you can split. I'm going to look here, things are worse for the honest guys because they're trying to do that by themselves. All right, and this Q is arbitrary. It's an abstraction, but it's supposed to capture reality. Then in a period of 10 seconds, there should be a maximum number of times you can call a hash function. Okay, called thing 2 to 32 or something. Okay, it's an abstraction, approximation. It's an abstraction of the thing, right? Then you can. Okay, so we're talking about this random, trials, right? Just trying to solve a proof of work. Modeling as a random oracle is going to be a random thing, so I can talk about random variables. Okay, you can represent, we have these random variables. So X is for like the good guys. This should represent that around I, some honest party obtains a proof of work, gets lucky. Z, I is for the bad guys, all right? And the Y random variable is just one guy. Okay, this is more stringent than the X. And again, what we'll try to do is compare these two things. Okay, intuitively, as long as Y is bigger than Z, right, the good guys are gonna win. They're gonna be able to install their own blocks, get a common view and so forth. Now, this is for one round. If you have a sequence of consecutive rounds, okay, they should have something like this. Okay, the sum. And then you can talk about expectations. And this notation is a bit heavy, maybe, but it's not that difficult. The expectation would be, some guy, some A minus T honest guys, Q queries, right? That's the probability of getting lucky. So that should be times S, there's the number of times, number of rounds that they can try, you get something like this, right? That's for at least one, any honest guy. This is for just one guy. This is a more stringent event. So you get something like this, just smaller. And this would be the expectation for the bad guys, similar to that. Okay, and if one assumes, remember I assumed that the number of bad guys is bigger than the number of honest guys is bigger than the number of bad guys. Okay, assuming lambda equal to 1, so then you can see, right, that this is going to hold. Okay, comparison between expectations of these random variables. All right, and so now we are off crypto. So now everything is probabilistic analysis. We're going to play around with these, random variables and try to figure out the work conditions, things hold, and so forth. And that's the proofs that we're going to have to skip. Okay, so let me at least mention what the typical notion is. This would be a good situation for us. So we call it typical. Before knowing this it's going to happen, right? We should not have called it typical, but it turns out that it happens all the time, so we call it typical. But it's a good situation for the good guys, and it's saying, this random variable is pretty close to the expected value. Okay, same with the y variable, same with the z variable. And we are bounding the z variable, right? So we give it a little bit more slack, but it's still bounded. And we have to assume also things about the hash function, which the random oracle guarantees. All right, and it turns out that we get this theorem, and this corresponds to the version of the theorem, the version of the paper that says that these typical executions happen always, that means with this probability. All right? And we argue binomial distribution, Chernoff bounds, and so forth. And that's how we show it. All right? So we show typical executions happen always, then we go to prove these other properties. Given that typical executions happen, how do we prove this? Okay, and we call this event corresponding to the y variable, the event that only one honest guy got lucky. We call that uniquely successful round. And the intuition is what I mentioned before, that you have these parties, with blocks and so forth. They might have different views, but at this point, just one guy got lucky. All right, so in that case, the views of all the honest parties coalesce. And this has been called later a convergence block. Right? Everybody gets into the same page. All right? And we can show that this common prefix property, holds with parameter omega kappa. And there's a proof. It's usually by contradiction. You look at the situation where it could be a branch, last honest block, and what happens here when some other honest guy happens, I'm gonna skip this. You get into a situation like this, we're going it by contradiction, right? Then you will get that the z is bigger than y, but we know this, and if we plug this expression, if we develop these expressions, right, for this to happen, you get this sort of expression, which is a contradiction if we assume the following. So we have a bunch of parameters, right? We assume a bad situation. We assume a bad situation happens, and we see what the conditions are to be satisfied with all these parameters, and that's a contradiction according to what we assume. Okay, so it's a very detailed proof, but that's just to give you an idea of how things work. So the conclusion is that the common prefix is going to hold with our only probability, in the honest majority assumption, where the delta value satisfies that, and they have a meaning, right? So at the higher level means that the probability of two honest parties having different chains, right? So parties have chains, they're going to prove K order kappa blocks, and they're going to be looking at this prefix, right? The probability of those, they not looking at the same thing is negligible, right? And the idea is, the intuition is that, we have these events, right? So they're competing, the bad guys and the good guys, that for every time a good guy, and that situation where everything coalesces, is lucky, the adversary has to compete, right? He has to produce another proof of work, right? To be able to maintain this split situation, and by requiring that this event is bigger than this, then that's how we get the proof. Right? That's a very high level. It has a bunch of details, and you can look at the slides and the paper. We do something similar with chain quality. But the observation here is that what is it that we would like? We have a bunch of parties that are corrupted, right? A bunch of parties that are honest, doing their own thing. An ideal situation would be that this proportion of guys is represented in the blockchain, right? If we have, say, H, the number of parties is H over N, so the proportion of blocks generated by those honest guys should be H over N. Okay? And it turns out that it's not achievable in this context. In fact, what we can show is that you can achieve it with, remember, mu was the parameter, the proportion of adversarial blocks in a sequence. Okay, you can achieve it with 1 over lambda. And remember, lambda was the value that you want the good guys to be over the bad guys. So we want lambda to be equal to 1, 10 to 1, right? In which case we have a majority. But if lambda goes to 1, then this mu goes to 1. So meaning in the very bad worst case, the adversary is going to be controlling, is going to be able to insert all the blocks. Okay. And it turns out that there is a strategy that makes this bound tight. Again, the strategy comes from selfish mining. I mentioned this A.L. Searer paper early on, and selfish mining is a strategy where the adversary mines but doesn't reveal what his results, and he keeps them, right? And when somebody, an honest guy, another guy publishes a block, that's where he publishes it, right? And this was the first most curious result, because everyone was talking about the half majority and so forth, right? And they showed that you need like 0.3, you can only tolerate 0.3 fraction, right? So here we are saying things in a different way. We still assume a majority, and we are saying you cannot get ideal chain quality. Again, that's the best you can get. Okay, this is what we obtain with honest majority. And there is a proof that you can go through, again by contradiction, and we get to something similar by obtaining that this Z was the random variable corresponding to the bad guys is bigger, as mu is this parameter that we have is bigger than XX by this mu thing, right? And you do the math, and you get a contradiction with respect to what you assume. Okay, so these are what we obtained, these are the conclusions, and this is already mentioned. This is the best you can do because there's an adversary strategy that matches it. And what this means is that in some sense, this rewarding mechanism is not incentive compatible because parties know, the honest parties are working, right? They're investing effort, but they know that their work is not going to be proportionally represented on the blockchain. Okay, so recall that we wanted to define this typical execution notion, prove these properties, we skip chain growth, and then modularly derive the properties of the application, just those of the distributed ledger. And this is what gets us to the second part, and that's we're going to talk more about applications. And I guess we'll stop for...
Yes. Thank you, speaker.